All right, Chapter 7 tests, logarithms and exponential functions. Let's get right after it. So number one, write the inverse of the function. So basically, remember, f of x equals y. And so I write that down. Then step one is to switch the x and the y. So just trade places. Rewrite it the exact same. Just trade those two letters. Now I have to resolve it for y. So I have to get that y all by itself. So and that kind of goes to the fact that when you graph this, it's always symmetrical about the line y equals x. So the ordered pairs are always switched. So to get rid of that square root, I'm going to square both sides. I'm going to square this side. And I'll get x squared equals, and over here will just be 3y plus 2. I need to subtract the 2 from both sides. So that'll give me x squared, take away 2, equals 3y. Then divide both sides by 3, and there's my answer. Y equals x squared minus 2 all over 3. All right, number 2, this is just recognizing which equation could be used to solve this problem. A school district has 2,800 students. So notice all of these have 2,800 in the correct position. And you're losing 8%. So when you lose 8%, you're going to do 1 minus 0.08 as your factor inside there, your decay factor. So it's actually going to be 0.92, and x is going to be your time. So the correct answer here would be D. Number 3, log base 2 of 1 over 32 equals, well, if you notice, 2 to the 5th power is 32. So to get 1 over 32, that's going to be 2 to the negative 5th power. Remember, negative powers are the reciprocals of the positive exponents. So the correct answer for this one is negative 5. All right, moving right along. Number 4, we start using some properties here. So this first one, I'm just going to rewrite in exponential form. So my base is 3. My power, my exponent is 4. And then this piece is just the answer. So that's exponential form. And that's just 81 equals 5x plus 1. Subtract 1 from both sides. And I get 80, divide. And we get x equals 16. Flowing pretty smooth so far. Number 5, one thing I always want to try to do is, if I can, I'd like to write the base I'd like to rewrite those as the same base. And I notice 4 and 32 are both, I can write those as 2 bases. So 4 is really 2 squared. And then 32 is really 2 to the 5th. So I've just rewritten the 4 and the 32. I'm going to leave the exponents the same for the moment. And now I'm going to use the rule where when you raise a power to a power, you multiply. So I'm going to have 2 to the 4x plus 8 equals 2 to the 5x plus 5. And now that they have the same base, you can simply just put the exponents equal to each other once you get the bases the same. And now we're just kind of using just some basic algebra. Subtract 4x from both sides. That gives me an x over here. Subtract that 5 from both sides. That gives me a 3 over here. And I get a final answer of x equals 3. If I was taking the test, I'd want to plug that back in, make sure that they work. It does. Moving on to number 6. Well, this time I don't believe that I can write 5 and 100 to the same base. I don't really know how to do that right away. So what I'm going to do is I'm going to take the log of both sides. So I'm going to do the log of 5 to the x plus 1 and log of 100. And then there's a rule that says, hey, you can, when you have it in log form, you can bring this exponent out to the front. And I can write it out front here. I can write an x plus 1 multiplied out by the front. So now you're actually gone. There is no more exponent there. And now I'm trying to get the x by itself, but I'm going to first be happy just to get that x plus 1 by itself. So I'm going to divide both sides by the log of 5. And I'm going to have x plus 1 equals, And when I divided that out on my calculator, I had roughly 2.86. And now I'm just going to subtract 1 from both sides, and I get x equals roughly 1.86. All right, next problem, I see logs on both sides, but they're the same base. So when you have the log of the same base on both sides, you can kind of just ignore those and just solve this algebra equation. So I'm going to subtract a 5x, subtract a 5x. That gives me 2x's on the right. So I need to get these constants or these numbers on the other side. So that's going to give me 10, and I get an answer of x equals 5. All right, number 10, or number 8, I should say. Getting ahead of myself. So the big idea here is I'm adding 2 logs. And whenever you add 2 logs with the same base, you can just shrink it into 1 log and multiply. So this is going to be log base 6. And now I need to multiply this x. I need to distribute it through both pieces. So that's going to be x squared plus 5x. And that's going to equal 2. And now that's in log form. So I'm going to rewrite this in exponential form. So I'm going to say 6 to the 2nd power, which is just 36, equals x squared plus 5x. All right, so we're looking pretty good. I'm going to get rid of this just because it's not necessary anymore. And I have a quadratic I need to solve. So at this point, I need to set it equal to 0, subtract that 36 from both sides, and now hopefully I can factor this thing, which I believe I can. If I factor it and use the zero product property, I should be in good shape. So 2 numbers that times together to make negative 36, add to make positive 5. I believe these would be the 2 factors that can do that. And when I zero it out, I'm going to get negative 9, positive 4. But you are not allowed, I'm not allowed to put that negative 9 right there. You can't have the log of a negative number. So this one is not a real solution. So correct answer here is just x equals 4. All right, number 9. So this time I subtract 2 logs. So when we subtract 2 logs, I'm really going to divide here. So this is going to be log base 4. And then I'm going to have 2x plus 6 divided by x minus 1 equals 1. And again, exponential form, 4 to the first power equals that thing. So 4 to the first power equals this thing. And now you got a couple different things you could do. You could times both sides by x minus 1. I a lot of times just stick a 1 under there, cross multiply, you get the same thing. 4x minus 4, 2x plus 6. I'm going to minus 2x from both sides. That's going to give me a 2x. And I need to add this 4. That'll give me 10. Divide, divide. And we get an answer of x equals 5. So number 9, x equals 5. Let's do number 10 here. So the big thing I wanted you to understand about number 10 is you don't see a base. And when you don't see a base, it's the common log. It's log base 10. So again, exponential form, 10 squared, which is 100, equals 3x minus 2. Add 2 to both sides. Divide by 3. And 102 divided by 3 is 34, I believe. There we go. Keep on cruising. Number 11. Number 11. This one, we ended up having to graph because it was pretty nasty. Tried to take a log of both sides, but it became really rough because there was x's on both sides. So this is one where I give you a hint. And I said, hey, let's graph this. So I want to graph y equals this side, and then y equals this side, and see where they cross. And what's going to happen is you're going to see the y equals 3x minus 2. and then you're going to see the exponential one, and there's going to be this crossing point. It ended up crossing at 1. It ended up crossing at 1.707. And I'm not sure if I still have this up here on Desmos. Let me just pull it up. Let's just get the old Desmos fired up here. So y equals 3x minus 2. And then y equals 5 to the parentheses x plus 1 power. And, oh, it should have been plus 2. I think. No, it was 3x minus 2. Oh, but then it was minus 1 in parentheses. This was a minus 1. There we go. And now when we zoom in here, you got to kind of zoom way in, you'll see x equals 1, and then you'll see 1.707. So those are both your answers for that one. That is a really nasty problem without graphing. So that's why I give you a hint and I said, hey, graph this one. Number 12. So number 12 says, hey, if you have a log equation, you're allowed to either put the power in the front or put this front up to a power. So I could rewrite that as log base 3 of x squared is 4. And now we just use the exponential form. 3 to the 4th power, which is 81, equals x squared. And when I square root both sides, I get x equals 9. So correct answer there was 9. Number 13. So this we start getting e involved here. And I can't really start taking logs of both sides until I get the base isolated. So the first thing I'm going to do is I'm going to minus this 5 from both sides. And I get 2e to the 3x equals 6. And then I'm going to divide both sides by that 2. So I get e to the 3x equals 3. And now we can sneak in, to get rid of that e, the natural log and e are inverses. So that goes away. And I have 3x equals the natural log of 3, which is just some decimal. Divide by 3, divide by 3. Now I have to go to my calculator. You can't just cancel those 3's out. We have to go to our calculator. And when I did natural log divided by 3, or natural log of 3 divided by 3, I got 0.3662. There you go. You could also graph those to verify if you're unsure. Number 14. Same thing here. I want to isolate. So I'm going to call this e to the x plus 1 equals 15. Just going to subtract that 5 from both sides. Now it's time to natural log it. And this goes away. I get x plus 1 equals the natural log of 15 minus 1 minus 1. And natural log of 15 subtract 1 was 1.708. There we go. Now we get into some word problems. A couple of these get a little bit trickier. So number 15, a house was purchased for 120 grand. After 10 years, it was worth 191. Assuming it was steady rate of growth, what is the annual growth rate? So remember, with any growth problem, these problems have a starting amount. Okay. We then have some sort of growth rate. We have our time component, and then we have what it finishes at. Well, I need to figure out what x is. This is not a logarithmic problem because I don't have a variable in my exponent, but this is an exponential growth problem. So what I'm going to do is I want to isolate that x to the 10th. So I'm going to divide this side by 120,000, divide this side by 120,000, and I get 1.5916 equals something to the 10th power. And to solve this, the easiest way would be to just get x over here. Let's just raise it to the 1/10. And we're going to raise this to the 1/10. And 10 times 1/10, well, that gives me x to the first, which is the answer. And when I put this in my calculator, be careful when you put it in. You put 1.5916 to the, and then be sure you put 1 divided by 10 in parentheses. And you will find out that you get 1.0475. Now, that's the growth factor, all right? But remember, when we do these compound interest type problems, or these money growing problems, it's always 1 plus the interest rate, or the growth rate. So the actual growth rate is just this part right here, which if you change it to a percentage, we grew at a rate of about 4.75% each year. So that would be my growth rate. You could also have done it with a graph. You know, you could have graphed this and then went to the table until you saw that number. But the problem is, this would have been between 1 and 2, and you would have had to make your change go like to the 0.01 maybe to be able to kind of see on the table that it happened somewhere between 0.04 and 0.05. You kind of have to get inside there. There was a couple other ways to do it, but that was how I did that one. Probably the fastest way. Bacteria is growing, so we start with 150. The growth rate is double. So 2 ways to think about it. One way is you could just put a 2 there. It doubles every single time. Or you could think about when you double, that's growth of 100%. So when you do your 1 plus your growth rate, it's going to be 1 plus 1.00, which again is 2. Now the tricky part about this problem is the exponent, because it's doubling every 4 hours. And we want to know, how much is that going to be after 2 days? Well, if you think about it, you know, you're going to double basically 6 times a day, because every 4 hours goes into 24 hours, 6 times a day times 2 days. So it's going to be a double of 12 doubles in there. It's going to double 12 times in 2 days. And this ends up being a pretty big number, 614,400. All right, number 17, the half-life of iodine is 8.1 days. Find the decay constant. So for this one, you can just use the equation 1/2 equals 1. So now I know I started with 1 or a whole. I ended up with half of that. It's e to the negative kt is the equation. We don't know k, but we do know t is 8.1. So now we have to solve that. Well, 1 times e is, I can just get rid of the 1. I actually changed 1/2 into 0.5. I'm going to do the natural log of 0.5 equals the natural log of e to the, I'm just going to reverse these so it looks a little more normal. And natural log of e are inverses. They cancel each other out. So now to solve for k, simply going to divide both sides by negative 8.1. Divide by negative 8.1. And I got an answer of k is approximately 0.0856 when I round it. And I said you could round to 4 decimal places throughout the chapter, so that was pretty good. Now I'm going to use that k in the next problem. It says, hey, use that constant to find out how long it's going to take 200 milligrams. So I want to go from 200 milligrams. I want it to get down to finish at 5, e to the negative kt, but I know k is 0.0856, but I do not know my t. That's what we're trying to figure out, how long. So we knew the start, we knew the finish, we knew the decay rate, but we didn't know t. So first thing is, I got to get base e by itself. So divide both sides by 200. And this was 0.025. Just kind of copying the rest of this down. And now it's time to natural log both sides. Natural log natural log, you guys are gone. To get t by itself, divide by 0.0856, divide by negative 0.0856, and I ended up getting t equals and coming right down, number 19. So any of these compound interests, you got to be careful on how it's compounded. This one was compounded quarterly, so I want to use the equation, the amount is the principal, 1 plus r over n, which n is 4 when it's quarterly, all to the nt, or 4t. So there's kind of the equation for compounded quarterly. And I wanted my money to double. So I wanted to get $10,000 with a start of $5,000. And we're going to have 1 plus 0.07 over 4 to the 4t power. So again, looking at this thing, I need to get my base by itself. So I'm going to first divide by 5,000. Divide by 5,000. So I want 2. I want it to double. Notice that 2 is similar to that 1/2 in the decay constant problem. The 1 plus 0.07 divided by 4, let me just crank that out and get one number just to kind of shore that up a little bit. So 1 plus 0.07 divided by 4. Well, that's 1.0175, all to the 4t power. And now we do have a variable in our exponent. We do have the base isolated. So I think now I could take the log or the natural log, doesn't really matter. Maybe I'll just do natural log because I feel like it. Natural log to both sides. And remember, I can bring the 4t to the front. And so 4t times the natural log of 1.0175. I just rewrote that right side because I knew that that's a log power I can use. And to get 4t by itself, let's just divide by this little fella and divide by him on the other side. I don't know why I put 5,7 over here. Felt weird. 7,5. All right, had to take that quick call. And I ended up getting 39.95. That canceled out. I got the 4t, and then divide by 4, divide by 4, and I ended up getting 9.99 years. All right, number 20. Suppose you invest $8,000. Now this one's compounding continuously. So this has its own equation. It's actually pretty nice compared to the other ones. It's the shampoo equation, the PERT equation. So I start with 8 G's in principal. I'm going to multiply by E to the RT, which R is 0.045. My T, from 18 to 40, that's 22 years. So be careful that all of this stuff is in your exponent. When you crank that out, you're going to get a grand total of $21,529.88.